Hi everyone. The next continuation for the part of Thevenin's theorem, we'd like to discuss on Norton's theorem. In today's part, I'd like to have Norton's theorem. Same numerical only I'd like to choose what I had chosen for the part of Thevenin's theorem. Same current flowing across 24 ohms, verify Norton's theorem is our question. For this particular one, we had to follow same 3 steps. But what's our first step is common. Remove that entire part of load resistance. That it is current flowing across the 24 ohms is our question. This resistance will become which thing? Load resistance. Remove that part by short circuiting. Whereas in terms of Thevenin's theorem, I would like to make this one as open. Whereas in this problem, I would like to make this one as short circuit. That's our first step. This one. Second step is nothing but when I make it short circuit, there's no chance of voltage here. Voltage becomes 0. But current flowing across that particular one, that current I would like to find out here. What's that current here? Norton current. Remember the thing? That current is nothing but Norton current or else short circuit current. That's the step you have to find out here. Second step. Same circuit but make that remove load resistance and short circuit this branch. Try to find out current. When I make it short circuit, that voltage becomes 0. When voltage becomes 0, resistance also 0 here. Parallel to the part of this thing, this circuit also will become short. It also becomes, there is no resistance exist in between this one. Why means this resistance is 0. Parallel to the part of this one also becomes 0. There is no existence of 12 ohms right now here. It becomes 0. Remember that thing. If any branch is short circuited, parallel to that branch, there is no resistance will flow. That it is, this one is a circuit right now. We can find out current now. That current is nothing but I Norton. I equal to V divided by R. We are having only 2 ohms right now. 12 is short circuited right now here. That's why the current here is 10 divided by 2 is obviously 5 amperes is the Norton current is our second step. The third step here is same location. What I shorted here, that location I would like to find out resistance. That resistance is also known as equivalent resistance or else Thevenin's or Norton's is same. When I would like to find out resistance values, if there exist any sources, try to make those sources to 0. That it is, if there exists voltage means I would like to make it short circuit. And we come across 2 resistance are connected in which connection? Parallel. 2 in parallel with 12 and obviously product divided by summation will give the information of Norton resistance. It's approximately 1.714. When I know completed 3 steps. Step number 1, remove the load resistance by short circuiting. Second step, try to find out Norton current. Third step, try to find out Thevenin's or Norton resistance. When I know all these 3 things, try to make it one equivalent circuit. That circuit is nothing but Norton's equivalent circuit. This circuit is connected in which connection? Parallel connection. Try to obtain the things. Norton current in parallel to the part of which thing? Norton resistance in parallel to the part of load current, load resistance, what I removed there. Observe this diagram. From this particular diagram, can you evaluate the parts of load current there? Simply, I know one rule. That rule is nothing but a current division rule. And our intention is I'd like to find out current flowing across load resistance. This thing. This one is a total current. Can go for the part of this one or to the part of this one. I'd like to find out this one. What's the formula? Current division rule formula here is total current, Norton current into opposite resistance Rn divided by summation of these 2 resistance is our current division rule formula. This arrow mark is indicated for current source. When I know the value of Norton current 5, resistance 1.714 divided by summation will give the value load current here as 0.33 amperes. Same also will be there in terms of Thevenin's. The duality of Thevenin's is nothing but Norton's here. Whereas in terms of that circuit, that one is nothing but Thevenin's equivalent circuit is a series circuit, whereas Norton equivalent circuit is a parallel circuit. That's the only variation. That's why this theorem is also known as dual for the part of Thevenin's. Remember the steps. Remove load resistance by short circuiting, find the things of short circuit current, and the third step resistance. All these 3 are connected in which connection? Parallel, and try to find out current. That's the only procedural steps you have to follow. When I know all these things, I'd like to go for the part of statement. it in a sequence. Statement for the part of Thevenin's theorem. Thevenin's, what I followed, same for the part of Norton's. In any lab network having number of voltage sources, current sources and resistance can be replaced with a single equivalent circuit is nothing but that is Norton current in parallel to the part of Norton resistance and load resistance. Yeah, only one thing. In any linear active bilateral network having number of voltage sources, current sources and resistance can be replaced with a single equivalent circuit, Norton current in parallel to the part of Norton resistance and load resistance. That's the only matter. This one is nothing but statement for the part of Norton's theorem. Whereas same statement I would like to follow for which theorem? Thevenin's, but it's a series circuit. That's the only variation. Remaining everything is common. That's why these two circuits are nothing but dual circuits. Yeah, that's the only matter. When I know all these three theorems, we would like to finalize one more theorem. That one is nothing but maximum transfer theorem. And in the next session, we would like to discuss that one.